Hello everyone, welcome. In this presentation, I'd like to give an update about the web application support with one running on top of Chromium embedded framework in the AGL platform. This is the agenda with the topics I'd like to talk about today. I will start by telling what are the goals of this effort, a brief description of the one architecture, why we chose CEF, what is CEF, and how are we using CEF on top of one, and make a demonstration of the current HTML5 image. So I work in Igalia. Igalia is an open source consultancy with HQ in Galicia, Spain. There are more than 100 engineers around. We work on web rendering and browsers such as Chromium, WebKit, WP, and Firefox, as well in other areas like compilers, graphics, multimedia, and kernel. We are the second main contributor to Chrome right after Google, and the second main contributor to WebKit right after Apple. The idea of having CF as a web backend is not new. There is a ticket that was created in 2021, but it was discarded back then. And when we were defining the 2023 roadmap for the web application support, CEF was mentioned as an option for improving the time that we take for doing a milestone upgrade for Chromium. So we decided to start a proof of concept of using CEF on one. WAM stands for Web Application Manager. It's the web runtime used by LG webOS project and also by AGL. AGL uses a fork of the original WAM. If you want to know more about AGL history and architecture, I suggest you to watch this first link that is a talk given by our colleague Dape in this year's FOSDEM, and also my talk from the previous AMM where I show how you can create new web applications and how we use the WAM architecture to expose system services and make them available for web application developers. And WAM is not framework specific. You can use any web front-end framework that you want. It has out of the box compatibility with standard web APIs since it ships everything that Chromium offers. It manages the web app lifecycle and has many optimizations for CPU usage, status monitoring, and memory management. It's a complete web runtime, pretty different of the goal of the CF project, as I'm going to explain in the next slides. And one works by leveraging Chromium infrastructure to create a runtime that launches and manages the web application lifecycle and offers pluggables that we can use to inject services that can be used by web application developers. And on AGL, it's a bit different from this image. Instead of the Luna, we use gRPC for communication, but the architecture is pretty much the same. And what our current implementation based on CF does differently is that we don't use the service and pluggable infrastructure provided by WAM. We instead override the web runtime interface provided by WAM, and we launch our own processes, manage the processes using CEF. And what we did in order to make one use CEF instead of the Chromium WebOS implementation was to extend one's base classes designed to represent a web application, and those are web app and web page base classes. We extended them and tied them to the closest representation that we could find in CEF. And this is CEF window delegate in the case of the web app. And web app is responsible for managing the application lifetime and display on screen. And CF browser view delegate in the case of web page, and this is responsible for loading and managing the progress of a web page and other web page related functionality. Now I'd like to make a quick demo of our current HTML5 image and then talk about our current status. As you can see, it's pretty close to the implementation using Chromium webOS. I will just go over a few applications. And the current status is that CF is already being used as a one backend, but not everything that we need is already implemented. For instance, we need to extend our application lifecycle management and handle applications go into background and stopping rendering, DOM processing, and things like this. And when we implemented the connection between the applications and AGL compositor, we reused parts of the Wayland window and Wayland extensions from the AGL1 fork, but we can get rid of this and use other ways that CF can provide for us. For example, we can try to use off-screen rendering instead of relying on CF's window management system, and then managing the surfaces ourselves and communicating with the AGL compositor. And now that I already spoke a lot about CF, I'd like to get more into what the project really is. So, as I mentioned before, the goal of the CF project is pretty different from WAM. CF is a framework to make it easier to embed browsers into applications as web views, or even creating browser applications based on the library it creates. One of the good things about CF is that it keeps up to date with the current milestone releases with a little delay, because the maintainers need to fix bugs and manage the releases. You can check out the top-level architecture description in the first link here. We also have a list of applications that uses CEF and a link to the project on Bitbucket. CEF is a project sponsored by Spotify, and they provide regular releases for multiple platforms. You can check it on their wiki. There are a few similar projects, but they didn't quite fit the requirements. WP and WebView are both based on WebKit, and WP is more focused on low-end devices, and WebView aims to be a small library that lets you embed a WebView in existing applications, but doesn't offer the window management and process management control that we need. I kept webOS was E1 because that's the Chromium webOS is the project that we are effectively replacing with CEF. There is also Qt web engine that's based on Chromium but relies on the Qt framework, and we have a couple of discontinued projects based both on Chromium and the Mozilla platform. So why did we choose CEF for this effort? Despite one being a very complete project and a proven technology, the milestone upgrades doesn't happen so often, and when we need to upgrade our fork from a milestone to a new one, there's a lot of time and effort involved. And CEF follows closely the release cycle of the Chrome project. This means that every 2 weeks, a new version is released, and the CEF version is usually a week behind. And also CEF is toolkit independent. This actually wasn't an issue because the Chromium provided Y was enough for our proof of concept. And it's an improvement on security, since we can, for example, use the current Chromium LTS milestone, and on this milestone we don't receive feature updates for 6 months, but we keep receiving security updates. So basically our updates on AGL side would be only bumping the Chromium revision with a minimum delta. And we could track both the LTS milestone and the current stable milestone. So when we upgrade from a LTS milestone to a new one, we are going to not going to have a big delta as well. CEF has a collection of tools for automating fetching Chromium and patching it. It adds itself as a part of Chromium source and creates new targets for the project. It generates a library much like what Chromium webOS does. CEF generates the libcef and the sandbox executable, and also generates the Chromium resource files. It provides a stable C API and provides a C++ wrapper library. Going a bit more on how CEF works, it provides two different runtimes: the Alloy runtime that's based on the content layer, and the Chrome runtime based on Chrome layer. And the difference between those layers is that the content layer provides the base API needed to render the web runtime, but doesn't provide any browser-specific implementation, and the Chrome layer offers more functionality, the functionality that the Chrome browser provides, for example, connection to the Google services, auto-filling and other browser functionality. It can use the Views framework or the native platform framework to manage Windows. And the Views framework is interesting because if we decide to do so, we can provide a way for creating native CEF applications in the AGL platform that uses the Views framework for layouting and managing the whole application. And each runtime implements its own a process and browser bootstrap logic, but this is hidden from the developers that use the framework. One interesting part of CEF framework is the provided interface to work with V8 classes and manage JavaScript. This is all coded that I needed to create the app service object that's created by one and injected in the rendering process to provide access to the services to the web developers. It is also pretty easy to handle function calls on the app service object. What this handling code does is basically check what function has been called and call the method that will communicate with the browser process. CEF also provides a minimal interface for inter-process communication, and here is what we do when we receive a start call in our app service object. And on the browser process side, when we receive an IPC message from the renderer, we check what was the call, and then we either start an application or get the applications list using the gRPC interface with the app launcher service. And that was basically it. There's still some work to do. We need to fix some known bugs in the current implementation, also to improve application lifecycle management, as I mentioned before, finish adapting the web app demos to the new gRPC interfaces, provide a way for bundling web applications, decide if we are going to still using the Wayland window application or if we are going to try off-screen rendering, and to bring back the browser as an application. We can do this either by using the Chrome runtime in CEF or by using the Chrome OS or webOS implementation. And that's it. If anyone has any comment or question, I would be happy to answer.